Okay, let's start. Good morning, everyone. This is fifth day, lecture 9 for the organic electronic material devices, this workshop. We have seen so far, at least we learned something about organic electronics and devices. In this lesson, I am going to talk about organic light-emitting device. Yesterday, Professor Gopalakrishnan says something about LED. Mostly, he might give you some overview of how LED devices are working. I think he might have given based on the inorganic based LED. So in this lecture, I am not going to talk about all the principle about inorganic. I am only concentrate on how the organic LED is going to work, what is the development is going on. And we already know that in the first lecture I said one of the practical application of organic electronic devices is LED that we are using right now. All the iPhone, the latest one is come with the OLED, and the AM OLED, you can hear about the term. This is so active matrix OLED. That's AM means active matrix OLED. So like this, the lot of product is coming. Is really useful. The main you can really realize the application of OLED means that only the size is small. Okay. If you're, I think you are mostly 30 plus. If you are in 1990, people are using the big CRT tube. You all know that how I don't know, you might have forgot. The CRT used cathode ray tube to generate all the lighting, everything else. I'm going to a little bit touch about how the technology is changing. I'm just talking about evolution a little bit and how we end up with the organic LED. That's my overview. And what is the material is behind them. Because everything is based on material aspect. What material is giving light emitting behavior? I'm going to concentrate in three types of material. One is fluorescence. Everyone knows the term fluorescence. The next thing is phosphorescence. The latest developments, TADF. You may not heard this term. Is it thermally delayed activated fluorescence? That's TADF material. I'm going to talk about three things. Then what is the current status? So this is I only concentrate only organic part. Okay. In this lecture, this is my 9th lecture. Okay, we'll stand here. It should be okay. Okay. I'll give the organic LED and the next because I'm going to these two lectures together. I'll finish it within 45-50 minutes, then continue with the interface engineering. Okay, then we'll finish this course. Okay, this lecture I'm going to talk about, everything is a solid state display. Anyway, the term itself is, you don't have anything liquid but our solid state display. Starting I would give the overview from CRT tube to, we have next is plasma display, you heard about them, then LCD display, then we come to OLED. Then what is the mechanism behind it? We already seen some overview, I'm just a little bit, we can do something. What is it? Is it battery issue? Any particular specific is it? I can go there, other side. Maybe I'll come this side. Is it okay? Okay, I'll come this side. This will be okay. Okay. So then I will tell you about polymer LED, a little bit, and materials for OLED development and development of it. So as I said, I will talk about these three generations of devices. The first generation is fluorescence material. The second generation of material is phosphorescence, the TADF, and then current development. This I will tell you. As I said, this is already seen this slide in the first introduction class. As I said, the OLED is basic devices like this. We have donor and acceptor. When you talk about any optoelectronic device, you got to remember that everything based on exciton. You heard about exciton. All the central point is exciton. You know how the exciton is generated in OPV device. We already seen this one in detail. In OLED, the same exciton is created because of electron and hole injection. If it is separated, is charge generated. If it is recombined, then light will come out. So everything starts from exciton is the central point. All the optoelectronic devices. In the OLED case, is a reverse mechanism of our organic photovoltaic. Here we generate holes and electron. That active layer material, that is the photoactive material, what is doing? It's recombined. We are forcefully recombine these two holes and electron. Then the exciton will recombine and the light will be emitting. The emission wavelength of light depends on your band gap of the material. That's I discussed already. Why the band gap is playing role in terms of absorption as well as in terms of emitting light. Okay, so band gap play. So here we use TPD and ALQ3 is a P-type and N-type material. We inject the holes and electron in this case, and at the interface, when holes are going to here and at the interface, the light will be external recombined, the light will be emitted. So here we inject the same mechanism otherwise. This is a very first stage of material, TPD and ALQ3P and N-type material. Okay. So this is a detailed mechanism of this one. All this device, optoelectronic device, at least one electrode should be conducting, because even for OPV, the sunlight should be enter into the active layer, that should be transparent. In OLED also, the light should be emitted through the transparent. So one electrode should be transparent. That's why we choose always ITO or FTO. Now recently the flexible, we are trying to use graphene. Graphene is another term, is this transparent electrode. So most of the cases ITO. Okay, all this transparent anode, that should be anode, because the work function of ITO is close to the hole. Okay, normally. Then we have a reflecting cathode. The reflecting cathode is that even though the light is traveling everywhere, all direction. When you go to the other side, even it will reflect back to the things and come back to the transparent light. Okay. So there are five, the mechanism, there are five processes. One is charge injection, both in hole and electron injection. Okay. So we need to make sure that the hole injection, the barrier, because this is HOMO level, this is LOMO level. We need to adjust the barrier. This is a work function of anode and this is a work function of cathode. So now you might get a difference that when you talk about metal, I talk about work function. When you come to the semiconductor, I talk about the term is called valence band and conduction band. In other words, it's called HOMO level and LOMO level. HOMO, I'm repeat that, highest occupied molecular level, it's equivalent to valence band. LOMO, why we coined is lower unoccupied. The levels are still empty, so that when light hit, the electron go to the empty level. If there is all are filled up, then again filled up state we can't. Nothing cannot go to conduction band, because when the electron goes to conduction band, then only it can start conducting throughout the material. Okay, so that is when we deal in the first class. Okay, so for hole injection, we need to make this barrier as small as possible, and in electron injection, we need to make this one is smaller. That's why we use the interface layer in both cases. When they travel through this one, and at the junction, the electron and hole mix. Again, it will form when the positive and when the hole and the electron is come together, it will make an exciton. Again, you remember what is an exciton? It's a bounded positive and negative charges is called exciton. When the exciton is formed, then it eventually is recombined and emit the light. So this is a basic one, charge injection, then it should transport and it should recombine, and the exciton formation, then exciton emit light. So this is a mechanism is simple, looks like simple. How we can implement this one is a device. That's and what wavelength you want to emit. That's the one we need to fine tune as a device basis for device engineering. Okay. Okay. Now we need to go. This is the Jablonski diagram. A little bit say about what is photophysical process. I think most of you know. I just a little bit explain what happened. So this is ground state. We all know that when the atoms are not excited, it's preferred ground state. Okay. If you want to do some work, we go to excite it, then it will always give out the energy will come out the things. So in what level it come out, it depends on the material's property. Everything. If you give everything stay in the ground state, when you give energy, depends on the energy it absorbs, it will go to the S1. S1 is the minimum energy it can accept. That's the energy is defined by the band gap. Okay. If the incoming energy is above the band gap, then only it starts exciting. Otherwise, the molecule or whatever the organism, it doesn't absorb anything. If the energy is, the band gap is minimum, this is the one. S0 to S1 is the band gap. If the incoming light is, the energy is more than this band gap, then it will excite, it will go to the higher state. If the higher energy, it will go to the higher state. Again, S1, S2, there is a lot of states there, depends on which level, KL, M, and cell you consider. And when it emit, anyway, it's naturally all the things goes, it won't stay in the excited state, always come back, prefer to come back to ground state. When it comes to ground state, it will emit energy. That's why we're getting light, all based on, all the fluorescent light based on this fluorescence construct. This is absorption, this is emission. And sometime if you have more energy, when you go to the thing is, when you go to the higher energy state, it will, whatever the electron go to the higher state, it will always little bit relax and come back to the S1 state. Then from here onwards, it will start emitting, recombine. It will come to the lower energy state, unoccupied state, then it will recombine. Then that's why the fluorescence will get uniform. But we will get to some others upper state, and that's why some of the fluorescent lamps are somewhat distributed. But in laser, we induced only all the similar wavelength. That's why the laser lights are so intense, because all emit light is in the same wavelength. That's why the light induced. We'll get a same, that's intense light. But here we can little bit upper lamp, the light will come out from even not only this one, little bit above state will come. It's a combined collection of different wavelengths. That's why it's a spread out, all the things. This laser you can say it's a sharp and we can travel a lot of time. And also in the case it can also convert into triplet state. Triplet state is another state of energy. Then when you convert to this intersystem crossing triplet state, again come to recombinations. This process takes little bit some more time. This is fast. When you come to go to other state and come back to other state, it will take delay the process. If it is more than micro nanosecond, this will process in microsecond actually. That's why it's called phosphorescence. Phosphorescence is the same as emission, but it's delayed emission. When you have delayed emissions, we can light for a long time actually. So even sometimes, even if you switch off the input light, some of the things emit light. One of the example is one of the insects emit light during night time. Okay, that's how the same chemiluminescence the light will emit. So those things are example of phosphorescent things. And in triplet state also, some molecule have the many triplet state, and that also it directly absorb to go to triplet state and emit. And one thing is we notice that when you go to fluorescence, when you emit, what is the probability of getting the electron go to singlet? So when you directly go to singlet state emit, this is called singlet emission. When you go to triplet state, then emission is called triplet emission, the phosphorescence. So if you pass one light, go to singlet and emit a singlet energy, there's only 25% only come at fluorescence. Remaining 75% is phosphorescence. Why? If you have the frontier orbitals, okay, if the electron is two state, right? So because the outermost orbital is one spin up and spin down. So both spin up and spin down arrange either one up and down normally. If both are up and down, its spin is 0, then it's just total spin is 0, then it's singlet. So another case is both can be up, both can be down. Another state is in between state. So if there are 4 states, out of 4 states, this only is 0. Remaining spin up and the remaining both are spin down. And this is not exactly cancelling out. This also contributing to the triplet state. So out of 4, the 1 is singlet, remaining 3 is phosphorescence. So if it is a material is fluorescence, we can extract only 25% of fluorescence energy. Remaining 75% goes to phosphorescence. That's why the initial stage when the fluorescence lamp is there, this is not effective. We are getting the internal conversion efficiency, quantum efficient 20%. That's why we go and develop the why we are going for phosphorescence means phosphorescence got 75% emissions for one frontier orbitals. So we'll discuss about all those which material can provide this fluorescence and phosphorescence in detail. Okay, I think now we understand why the phosphorescence is more efficient than the fluorescence material. Okay. What? Yeah, there you can. Which you are talking about this one, right? If you say this one exactly cancel out, what is the middle configuration is it not exactly cancel. It's in the middle, opposite when you do the things. I will come back to this one later. Okay. these are some of the light emitting diodes product. What is a, this is a pure white lightning, and some of the TV cell and brown. This already we have gone through this one. And next thing is I'm just to give just evolution of this light emitting device. The very first example is people use CRT tube. CRT tube only, it's occupy a huge space. So the basically how, so any of you know about the mechanism, this is the very first one. So anyway, just to give okay. In the CRT tube, what's happening is a made cathode ray. This is a tungsten based filament, it will emit electron. We are emit electron beam. The electron beam, which when you hit the fluorescence like a phosphor, the screen, it will generate the light. Okay, so it depends on the material. The deflecting coil will deflect the electron. According to that, we'll get image. It's basically on generating. I'm trying all those things. Okay, let's try it. Okay, so that's a CRT tube. Basically, it's based on electron gun. When it strike on the phosphor screen, we'll get an image. Okay, this is a very old technology. After that, plasma screen. Plasma is. Can you do anything? This back side, can you switch off this one? Huh? Hello? Hello? You will move banana. No, now it's no sound. Now it's no sound. Okay, but when the recording is here. Okay. Okay, then now it's audible, right? Yeah, it's audible. Okay, we'll try it. Okay, the plasma is, you know that this plasma is another state of material. It's a plasma state because the plasma in the TV, what will happen? There is a small plasma cell is there. The plasma cell filled with some gas, either neon or argon gas. So when you apply the electric field, the gas will become plasma. So it will emit the UV radiations. UV radiation don't have emit. When the UV radiation and also this plasma cell will coated with the phosphor material. You know the phosphor material is fluorescent material. When the UV light will hit the phosphor material, it will emit electron. Okay, it will emit radiation. So the color choosing is depends on which phosphorus you are using. Okay, according to the phosphor we are using, we'll get different radiations. Again, I'm saying that all the light emitting device based on only 3 color. We only make only 3 color: red, green, blue. So only the 3 different combination of these 3 color we can get whatever the color we want. We have 3 types of color inside. Each pixel consists of 3 small pixel which have a different blue, green, blue, green, and red. Okay. So when you apply this one, the plasma emit UV rays. The UV when you strike on the phosphor emit, it emit the radiation. That is a principle of working in the plasma screen. So this is, you can say there's the color emission of light depends on the type of phosphor we are using. So by varying the intensity of the input electric field, we can change the color of the things. Okay, whatever the pixel you want. So next thing is LCD. So LCD is working on the principle of liquid crystal display. We heard about term liquid crystal display means by applying what the principle of liquid crystal display, when you apply electric field, so the orientation is aligned changing. So it's basically working on the principle of blocking light, because here we heard about what is polarizing light. Polarization light means you know that when light travel, it will vibrate in all directions. Then when you come out the things, everything is something we count something clear. Suppose if the vibration we make it is a single plane, so then everything will focus. We will get only at least one light will come out. It should be clear. When it's compound all the component, then it will capture and things will be blurred. We can see the example of how the polarized light is giving the clear image. When you have the frog on the light, because of the light reflection is all direction, we are not getting the clear picture. When you have the polarizer, we are getting clear picture. That's a polarization. So here in liquid crystal display, the input light is become polarized light. That's why they have used polarizer first. Then at the end, they use another polarizer to see specifically which light you want. So basically, it's working on the principle of blocking light. Okay. So this is basic LCD technology, because here if you say the light is coming through, when this liquid crystal is directly changing the direction, when you apply the electric field, if you want to have the light is transmitted, you apply electric field, it will twist the things at 90 degree, then light will be passed out. If not, the light doesn't come out. Okay, the things are the liquid crystal, how is okay make? When you apply the electric field, it will change the direction, then you can see the light, otherwise no. So this principle is simple. How we are applying to the device, that's a challenge. So here we can see what are all the components inside the liquid crystal means. We have the ITO backlight. The liquid crystal display always have one standard backlight. The backlight can be LED or anything else. It always emit light. The light coming from the backlight, which light should come to the front, which you are seeing, that will be determined by your liquid crystal. And liquid crystal, according to what is the TFT we are using, we can select which pixel to emit light. That will decide by your TFT here. Actually. So this is your liquid crystal. When the white light is, when the polarized, this is the polarizer. When the polarized light allow only the polarized light towards the liquid crystal, this is another polarizer. If you see this polarizer and front polarizer, both are in the crossway. Because this polarizer, when you want to see the light, this liquid crystal will turn. When you apply the things, it will turn the path of light. Then when you turn the light, when it's, for example, if it is linearly polarized lights coming out, when the liquid crystal is working, it will turn to linear to vertical to horizontal. The horizontal light is come out. Depends on the color we are using, we can get the same color. Okay. You can compare this LCD into the previous plasma. Plasma concept is different, where the plasma is reflecting UV light. The UV will hit the phosphor. The phosphor will give the color of whatever you want. Depends on which phosphor we are using. Okay. The same thing we use in CRT. You can imagine how the technologies evolution, the developing CRT to plasma, then LED, then LCD, then LED now. LED is another simple, entirely different concept. These are based on exciton. Okay, these are all no exciton involved. Okay, so now we come to our LED. I think you will get some idea of how these things are working. Okay, in LED we use both the whole transport layer, electron transport layer. The emissive layer is the photoactive layer, where we generate electron and recombine and generate the light. Okay, so here we use at least like what we have seen in the organic photovoltaic. Here also we have used 5 layers: cathode, anode, whole transport layer, electron transport layer, then middle emissive layer. All 5 layers is a basic one. And also we are going to see the many layer. That's because of fine-tune the efficiency of this cell. We can use some blocking layer. I will come to that. What is a blocking layer again? So you see the very basic one, 1, 2, 3, 4, 5. And these are all the layer, whole transport layer. There are variety of things, diamine and TPD, all NPB. See, if you see all this material have the common property of very deep HOMO level, because the HOMO level should be matched with the high work function of the anode material, all those things. So the electron transport layer is low valence band, all those things. So if you see this one more on acceptor based one, all NN type will be there. Okay, all these things, electron transport. This is a emissive layer. Emissive layer is ALQ3 and rubrine and CBP, and these are all some of the things. It's called emissive layer of all these things, some example. And if you see the evolution of this LED, we can initially the people taught with the EML. This is only 3 electrode. When you start one, only put active layer and put electrode. They have very feeble emission. Okay. Then they found that they little bit improved only whole transport layer and emissive layer. They didn't use any electron transport layer. That is in 1885. After that, the very doped one, they use whole transport layer, emissive layer, then doped emissive layer. Where they are doing doping means doping will improve the mobility or conductivity of the emissive layer. That's why people are doping. Then here somewhat sophisticated multi-layer device. Here they use the anode and cathode is standard for injecting charge carriers, the middle layer doper. Here this is hole injection and hole transport, and hole blocking and electron transport layer. What do you mean by hole blocking layer is when the exciton, when the holes are when the holes are we are injecting, this side is electron injecting, those electrons which is not recombined, it will go to the cathode side and get recombined. That will be a detrimental effect. We want to avoid the electron reach the cathode the holes reaching the cathode, because if you inject a hole from here, it should be recombined. It's not go there, then it will recombine. So near the cathode side, we have to block the hole. Otherwise, the hole will combine, go to the electron, means it combine, it will be lost. Your things are affected. So to block the hole in this electron side, because in this side only electrons should come out, holes should not go there actually. So to block the hole, they will have the hole blocking layer. Same way, the anode side we have to stop the electron. So they have an electron blocking layer. So in anode side, the hole should be injected at the same time, the electron should be blocked. Okay, that's why that is some more extended version of this device architecture. We have instead of 5 layer, we can make 7 layer in this case. So other one is PI junction is a P-type and insulator N-type OLED. They have P-doped and N-doped, because now they have more sophisticated to improve the mobility of the material. They are doping. We know that in silicon also we do the doping, because silicon intrinsic is not conducting. We specifically inject the impurities inside. For example, for P-type we inject boron, because you know that boron is only 3 valence electron, 1 electron become vacancy. For creating N-type silicon, we inject phosphor inside, okay? Because silicon is 4 electron, phosphor is 5 electron. Out of 5, the 4 is bonded with the silicon, remaining 1 is free. So we can have 1 free electron for 1 phosphor. Like this, we can create N-type or P-type material, okay? So these are all evolution of the device fabrication. Then all those things, development is happened from solid state light link to, so different devices. Now is the champion is mobile, only we have iPhone and Samsung mobile. Okay, we saw that how is the mechanism and what is the material because something. And we see how we define this performance. I already gone through the photovoltaic, what is the characteristics, tell you that, which is more efficient. Like this in light emitting device also, this is some of the factor which tell you that, which if you characterize material, what type of material we need to characterize to see that performance. First thing is efficiency, as I said, quantum efficiency. In OPV, if you say that how much electron we are generating with the photon, right? If you have 1 electron out for 1 photon is 100%. Normally we won't get 100%, we maximum will get 80 or 90% only. In OLED case, opposite. How much photon we getting out, giving the electron, because we are injecting electricity, holes in electron, we get a light out. So how much light you are getting output with respect to how much injecting. So that is your efficiency of here one. So basically you have two, one is current efficiency, other one is luminance efficiency. There are two efficiency. That is for emitting. Then other things, current density will tell you that along voltage. And also one more thing, we need to emit light at very low voltage. If you have any very low voltage, that is an efficient device. That is called turn on voltage. At which voltage it turn on, that's called turn on voltage. That should be, the good cell will give the turn on minimum voltage. That is one more factor. And color purity. And also the emission will be very short color. So that also sometimes, some material you can see that it will have the broad emission. Broad emission, broad absorption is good for photovoltaic device, but in OPV, in organic LED, we need to have very sharp emission. Okay. And lifetime. Lifetime is, here we say that 50% of original efficiency. In organic photo LED, we saw that we have a different type of lifetime. Standard is T80 or T90, we have seen differently. Here we defined as 50% of original lifetime is called lifetime. So these are all some of the factors which define. Current efficiency will define by candela per ampere, and luminous efficiency is luminance per watt. So this is a 2 unit, you remember, okay? So these are all the factors which define the performance of organic light emitting devices. Okay. Next, what are all the required property the ABC layer should have? The one is, as I said, the material should be high purity. That's why most of the organic materials are small molecule. When you have the small molecule, we can have the high purity because the organic molecules have the flexibility to have the only finite, we have the finite molecular weight. We can, and also we can maintain the high purity by doing the crystallization process. And also they have the high thermal and oxidative stability because it should be stable enough when you're working on a decent temperature actually. Then it should have a expected high charge transport property at the same. In other words, it have a decent mobility, reasonable. We don't need that much high mobility. It's not a transistor. Transistor only we expecting very high mobility. But here is a decent mobility of charge carriers. And then luminescence quantum field. Yeah, it should be, the quantum field is how much the light is emitting about given how much injecting electron. That's a quantum field. Then you have a high color purity and stability and high, it should have the ability of high quality of thin film making because these are all working in spin coating property and we are all evaporation technique. It should make a very uniform and pinhole free film because if you have the pinhole free, that will introduce a defect, then eventually the device can be degraded. So it should form a very high quality film. Okay. So these are all some of the characteristics for the good organic semiconductor material. Okay. So this is another one. Will tell you that this is very initial stage of where the polymer LED. Polymer LED is nothing but the emissive layer is polymer. Okay. So now we are mostly moving on to OLED, means only small molecule because small molecule only we can have the high purity as well as the color purity is very high. When you have the polymer will give different molecular weight. We have different batch. We have different quality of material. Anyway, this is very first time. The first demonstration is happened in polyparaphernalia is from CDT with the Professor Andrew Holmes and Richard Friend is still working in CDT. He is the only one demonstrated the light-emitting device and they have the spin-off company CDT still is running. Andrew Holmes is a synthetic chemist. Originally he was in Cambridge before. After that, in 2006 he came to Melbourne and he started organic electronics research. Actually, he is my supervisor when I am doing the postdoctoral in Melbourne University actually. And he developed the OLED first. Then later the material, because he is a material chemist basically, all the conducting polymer. So he developed not only for OLED and all the type of transistor and everything else. And we maintain the lab is a #1 lab in Australia actually. So this is the first OLED developed in CDT lab based on polymer actually. Okay, now I come to the next, what are the different organic semiconductors available here? Okay, here you see that I said 3 generations of material I talk about. What is it? Why we now we are third and there is 4th generation also coming. The first one is based on fluorescence because as I said fluorescence is simple. You just go to singlet site and emit fluorescence. As I said, this is only 25% efficiency. So this one we are getting internal quantum efficiency is only 25%. Okay, it's only singlet site. That's why the second generation was developed where you use the phosphorescence material. Phosphorescence material have the chance of emitting IQE is 75%. Is go to intersystem crossing and emit light through phosphorescence effect. This second, that's because of this IQE is limited. We generated second OLED, and again we have the phosphorescence have the color purity and stability issues because in the phosphorescent material we have this type of transition metal, iridium and platinum, everything. So that will make the stability issues of long term. So the third generation material is called TADF material, that is thermally activated delayed fluorescence. Again, this not it involved the triplet state. Again, is a fluorescence because in this case, what we are doing is they designed the material in a way that the singlet energy levels and triplet energies are very close to each other, so that when the electrons go to the singlet state, eventually if you go to the triplet state, it will again go back to the singlet because this energy level is very, very small. They make it so that instead of coming to triplet to singlet state, it will go back to the singlet state and emit. So all we are expecting here, all the 100% fluorescence emission is coming. Because the main problem of here is that triplet and singlet energy levels are too big. When you compare this difference and this difference is too small. So that it will give immediately go to the system crossing and reverse system crossing. It will go to the triplet to singlet state. That's why this material is called TADF. So in the material design itself, we can design the material in such a way that the material, whatever the material go to the triplet state, it will go back to singlet state. That means if you make a chromophore instead of a planar, if you make a twisting molecule like instead of plane, it will make a 90-degree turn like this. If you introduce a twisting in this one, the material will become, the energy gap will become smaller. If you see this material, the carbosol is one of the material which gave the triplet energy level, vertebral. So when you have all these levels or everything, if you have this planar, this is twisted again, this one. Like this, the material design we introduced like this with the nearby electron repulsion, it will make a twisted automatic. This is one of the good example for the TADF material, which have the triplet singlet energy gap very, very minimal, and will eventually it introduce into the reverse intersystem crossing. Okay, so that as I said, minimum the 78% is going to the phosphorus. Again, it will go back to the fluorescence and will get 100% efficiency, theoretical efficiency. Okay, now this first generation OLED is based on completely fluorescence. Here IQE is only 25%. These are all the materials which go for only fluorescence material. These are all some of the benchmark devices which are used for in fluorescent device. This is for blue emissions for high band gap, and this is for medium band gap green emissions, ALQ3, and DC JTB is for red emissions. So all these three materials have only maximum quantum yield is 25%. Okay. Next thing is I am telling that this is fluorescence. This fluorescence majoritarily will go to the only fluorescence. It doesn't go to the intersystem crossing. And in phosphorescence, most of the things in triplet harvesting, it will go to the triplet state. And this is the things because of what is a singlet state is only one state is possible. After the intersystem crossing, the triplet and triplet pathway is if it is equal to 0, then magnetic potential, then this combination will give remaining three states go to the triplet state. Again, this triplet state will come back to the phosphorescence scale. So here is only one state is coming out with the maximum efficiency of 28%. Remaining is 78% is go to the exciton generating this phosphorescence case. Okay. So because the IQ is very low, so generated second generation OLED with the phosphorescence film. All this phosphorescence material will involve the inorganic like iridium, some the high atomic number material, iridium, or mainly is involved in all this. Iridium complex is mainly giving the phosphorescence material. Even the organic one, amine group, this is for green emissions, this is for red emissions, yellow, and if you see all these combination iridium, all this high molecular weight compound, inorganic compound, all the platinum and iridium complex will have the more efficient phosphorus because it will induce the intersystem crossing and go to the triplet state. So this is a representative for phosphorescence material, and to give the quantum yield of EQ. I am talking about EQ. Again, I am saying that EQ is something different from IQ. IQ means it will give whatever the in phosphorus, because whatever the light is absorbed by the layer, then whatever the emission created. Because when you do whatever the photon is actually absorbed by the layer and how much electron is given, that is called IQ. But EQ means the total influx. Because when you have the total influx, some of the radiation will be lost because of the absorbing the whole transporter, electron transporter, and glass. Everything will absorb something. That things will not take care of in EQE calculation. But in IQE calculations, those the stray absorptions will be subtracted, so that exactly what it get absorbed and what it generated. That is IQE. EQE means just what is incident and what is come out. When you take the incident, when it go to the absorbing layers, much of the layer is much of the photon will be lost because of the absorption of ET layer and also glass. Even the ITO glass also got some absorption. That will doesn't care of when you calculate EQE. Okay, this is third generation material which is designed. Some of the first one is CPC layer. Here we made this material design is they make only the triplet at the singlet energy level is very small. That's why when it go back to the triplet, it will again come back. Because this energy, when you have a small thermal energy, it will come back almost singlet and triplet energy same level. This is a very good example of TADF material things. Okay, so this is we keep this energy gap as small as possible. Okay, so that the whole phosphorescent material, the 78% will go back to the fluorescence and emit. So this is TADF. So this material only so far they developed is this actually result they started working on later in 2012. Then now they make use a commercial product out of this one using TADF material. So this is carbazole material and CAPs. These are all very good TADF emissions. So the material design for the TADF is it should have a very small energy difference between the excited singlet state and triplet state. And some of the carbazole based molecule have the very higher triplet rate. You know that carbazole molecule, this is 2-phenylene crossed with the linked with the N-carbazole, this is called carbazole unit. This one have the higher triplet energy levels, okay. And also we have the triplet energy gals, whatever we are getting, it should be very homo level and lumo level should be orthogonal, okay. In other case we make it all planar, but here is orthogonal. That makes this triplet singlet energy level is very steep small. Okay. So now I am saying that some of the recent development is going on in efficient OLED. So now anyway, all the display devices we use 3 pixels like red, green and blue. So there is some of the OLED is emit only white light. That's for only lighting purpose, not for display purpose. That's white OLED is another example. And we indicate efficiency and lifetime of OLEDs. Anyway, we design all the material. Finally, it should work for long term and efficiency should be light because at low apply voltage it should emit light. That's one of the criteria for the best efficient device. And also red and green is a phosphorescence. Still one of the great challenges, one thing is getting blue light, because blue light means it's a very high energy. The energy gap will be very high. When you have the high energy gap, always it have the degrade first. When you have high energy, the material get degraded. That's why it's still challenging. We'll get a very good phosphorescence blue emitting light. Still, the blue emissions are still based on fluorescence. We can't get that much efficiency comparing to other green and red LED. Blue LED is still challenging actually, so because of the high energy. So this is one of the number of unit substrate they are developing with the VR. So keep on increasing this development of the OLED every year actually. And if you see that market of organic LED case, if you see the area, so normally this OLED is fabricated on polysilicon, this low temperature polysilicon surface. So that will, because it will cost overall, how much cost unit per million actually? These are only 600 million if got. So from 2022 they are expected that the production is shipment of this OLED increased by 1,000 million. It's close to 1 billion. So now this OLED is a growing market. A lot of development is going on in this one. Okay. This is some of the example of this current development one. I think I have give some overview of what is the development is going on, starting from your CRT tube to OLED, and what are all the materials used to first generation, second generation, and third generation. What is the current things and where we are now. We already go through, and how is the market is very bright. If you have OPV, still a lot of challenges to come out to the real market, but OLED is already in the market. But still they are developing for very cheap and flexible. Flexible is another one. Flexible means in future we can have the display of even the paper, e-paper. We can read the paper and flexible everything else right now. So that is coming out in this field. With this one I will conclude this OLED topic, and after this we'll continue with the interface engineering of organic semiconductor. Now if you can ask me any question in OLED. Okay, thank you.